Modern India is growing at a rate the world has rarely seen. With over 1 billion people and expanding industrial hubs, the country faces a constant, rising demand for electricity that the current grid can barely satisfy. To keep the lights on, the country depends on a massive logistical chain, importing coal, gas, and specialized uranium fuel. This creates energy dependence, where domestic growth is tied to the stability of global shipping lanes. Nuclear power provides a low-emission, stable baseload of electricity, but India faces a geological constraint. Its natural reserves of uranium are exceptionally small. However, the same geology provides an alternative. Within the monazite sands of the southern coastline, India holds roughly 25% of the entire global supply of thorium. The problem is one of chemistry. Thorium is fertile, but not fissile. Unlike uranium, it cannot independently sustain the chain reaction required to generate power. It essentially requires a separate starter fuel to begin the process. Because of this, India could not simply replicate the nuclear programs of other nations. It had to engineer a 3-stage pathway to convert its vast thorium reserves into a functional power source. In the 1950s, the architect of this strategy, Dr. Homi J. Bhabha, recognized thorium as the only domestic resource capable of providing long-term energy security. Bhabha's realization was that this wouldn't happen in a single step. He designed a sequential master plan that would require several decades of infrastructure development to complete. This strategy utilizes a closed fuel cycle. As this diagram shows, the spent fuel from one stage is chemically reprocessed to become the necessary fuel for the next, minimizing waste and maximizing the energy extracted from every gram of material. The latter is simple in concept. Stage 1 burns uranium. Stage 2 uses the resulting plutonium to create more fuel. And Stage 3 finally transitions to a thorium-based cycle. It is an intergenerational strategy designed to ensure that the end of one cycle provides the exact materials needed to start the next. The first step on the ladder utilizes pressurized heavy water reactors. These systems run on the limited natural uranium already found within India's borders. These reactors are the current primary source of India's nuclear power, contributing the bulk of the country's 8,780 megawatt installed capacity. But the most important output isn't the electricity. As the uranium inside these reactors is consumed, it undergoes a transformation, leaving behind a new element in the spent fuel, plutonium-239. While Stage 1 provides immediate power to the grid, its primary long-term purpose is to manufacture the plutonium required to bridge the gap into the second stage. This leads into the current high-stakes phase of the program, Fast Breeder Reactors. India reached a major milestone when the indigenous Prototype Fast Breeder Reactor at Kalpakkam attained criticality, meaning it began a self-sustaining chain reaction. The internal mechanics are sophisticated. The core uses a mixture of plutonium and uranium, bombarding a surrounding blanket of uranium-238 with fast-moving neutrons. This makes it a breeder. The bombardment transmutes the blanket, creating more fissile plutonium than the reactor consumes. Once the technology is stabilized, engineers will replace that uranium blanket with one made of thorium-232. The neutrons will hit the thorium and convert it into a rare artificial isotope, uranium-233. This material, uranium-233, is the final technical requirement. It is the only isotope that can effectively power the third and final stage of the program. In Stage 3, India will operate advanced reactors that run on a self-sustaining cycle of thorium and uranium-233. This phase promises significant advantages. Thorium is far more abundant than uranium. It generates less long-term radioactive waste, and it allows for a grid that is completely decoupled from international fuel markets. These benefits are the foundation of the Atmanirbhar Bharat initiative, which aims to reach 100 gigawatts of nuclear energy capacity by 2047. However, reaching this endgame is an immense challenge. Commercializing thorium-based reactors requires overcoming complex engineering hurdles and securing the massive financial investment needed to build a new generation of infrastructure. There are also persistent public concerns regarding nuclear safety, which continue to influence political support and the speed of development. Bhabha's vision has survived for over 70 years. If India can successfully navigate these technical and economic barriers, it will become one of the few nations on Earth capable of powering its industrial future using only the resources found within its own borders.